complete the square, when you have something in order p squared and order p, and you complete the square, you end up with an extra term that you have to subtract off, okay, and complete the square term. And this leads, and you can look back at the notes and see, it leads to a e to the I m x dot squared over 2 dt. Remember that this term came from this term plus the p x dot dt. This term came from this term by completing the square in p, and then you had to, this was a minus sign, you had to add this guy, okay? So you had this line and you added mx dot squared over 2 dt, and you subtracted it. And this, and this turned into just the p tilde squared. But then you were left with this. Okay, so I just reminded. Well, now you have to repeat the exercise, but the epsilon is there. Okay, I'm just guiding you through doing this exercise yourself. Well, doing every step. And what happens is you end up with a 1 plus I epsilon. Okay? So we have to just ask, where does this fact then show up? Where does the epsilon show up in the quantum field theory version of the story, which is just some n-dimensional version of what I've just talked about, where n is incredibly big. It's per term like this. What is it? Okay. So this goes in quantum field theory to an e to the, so an extra factor, which looks like this. So the first one is not going to surprise you. This, I'm just looking at the extra factor, right? Exponential with that term is just the e to the minus mx dot squared epsilon. Well, in field theory, the analog of the x dot squared is the phi dot squared, and remember, the analog of m is 1. So that's okay. But wait, there were other places where the epsilon was. This epsilon hails from the kinetic term in the Hamiltonian. But then there's just the potential terms in the Hamiltonian, which also got multiplied by epsilon. So they are going to be there, and so I haven't fretted about it there. They're not very subtle, but in other words, it's as naive as you might have hoped, which is that when the dust settles, the epsilon is multiplying the energy functional in phi space language without any pi's or p's or any of that. That's being integrated out. So, oh, good. That life is at least that good. And this thing is, say, m squared phi squared plus, whatever I'm multiplied for. So what does this do? This is sitting inside a path integral, which, in fact, I need to be more exact, leads to a path integral which looks like, so all of these epsilon subtleties, it's the naive e to the I action, but then there's this extra factor. Okay? So this is where the epsilon has ended up. So this thing ends up, what role does it play? It's again a convergence factor for visualize it. It's a multiple set of integrals. But their highly oscillatory integrand is a little frightening to see how it is necessarily well defined. But with this convergence factor, I don't have an oscillatory integral. In fact, for large phi, so I can think perturbatively about lambda. Let's drop it for a second. Even in the free theory, this m squared phi squared, so this is a sum of squares. This is not, it seems to be having either sign, but for large phi, which is where we're worried, we're integrating over phi from minus infinity to infinity at every point in space-time. But for large phi, this thing is beaten out by at least this term. Certain by this term. And all of these are positive quantities. So it's e to the minus something like for large phi, this is only getting exponentially down. That's all we're saying. In that sense, it's a convergence factor for this. Okay? That you are not at the mercy of some oscillatory behavior. So, in a sense, then, at this point, we say the thing that is hanging, we are not satisfied with, is the short distance subtleties that I've thrown under the rug. Things like, is it a discretized integral, discretized space-time, or am I supposed to think this is a continuous theory, or, I mean, all of that question is still hanging. Is something off today? Got that. So I just want to do an interrogation period and see what happens. So in fact, I think the only thing to see is, at this stage, that the only effect of epsilon, what is it that stops us taking epsilon to 0? Again, who's competing with epsilon going to 0? And the answer is, it's large phi. Okay. But from that point of view, this can be replaced by e to the minus epsilon if the only point that this, the only reason that epsilon cannot just be taken to 0 right off the bat, in other words, never have introduced it in the first place, is when all the dust settles here, that it is giving us a convergence factor for phi, for large phi, then that is just as easily done with this factor. So therefore, naive m squared phi squared goes to m squared with this epsilon. You know, whether I call it epsilon or I call it epsilon m squared, doesn't matter. It's epsilonic. I can talk about an epsilon prime, which is epsilon m. But the main thing is that where in the original formula, so here's the formula that we've derived with epsilon subtleties. That's what we're worrying about. And these epsilon subtleties can be summarized by saying, wherever you saw m squared phi squared in here, if you replace it with m squared phi squared, but with an extra minus I epsilon, then the minus I epsilon and this I, remember m squared appears here with a negative sign. So this with this I will just give you this. Okay, so just check for yourself that if you just replace this mass term with this combination, that you're just going to get back this behavior. Okay? And recall, this is form of epsilon in Feynman propagator. So recall that in the Feynman propagator, there's also an epsilon somewhere in that propagator. And the quick way of remembering what it is, where it is it's like the naive thing. Oh, I only remember this about, this is the naive propagator. And oh wait, there's an epsilon somewhere there. And the answer is, it's there, right? Exactly like the naive answer. This could be the retarded propagator, the advanced propagator. There are many propagators, as you've probably seen at the beginning of Peskin and Schroeder. But the Feynman propagator is that, okay? And that's just this substitution. Yeah.
But doesn't the epsilon multiply the derivative, so wouldn't that also be in the momentum term?
In the momentum term. This one.
Yeah, yeah.
Or this one.
Well, it multiplies both of those, and won't those give you like epsilon on the p squared when you find the propagator? For
No, in the sense that the p, if I were to Fourier transform this to integral, say dx naught, but integral dq p or something, right? Or hell, let me just do integral d more p. Okay. This thing would turn into p squared phi tilde squared. Okay, and oh, so that's what you're saying. You're saying this plus this, you'd have p squared plus so minus m squared, and the whole thing would have an epsilon in it.
mm-hmm.
Right. But yeah, so let me say that a little slower. In the end, we are going to where the we're only looking at the epsilon in terms of what happens for large phi. And let me see, for large phi. Oh, sorry. No, got it wrong. It's this. This was absolutely crucial. This is not the action. It's the Hamilton. So it's actually p0 squared plus it's minus. I'll just get the relative sign correct. Choose whichever one I want. But it's this plus this plus this. Okay. It's plus plus plus. again, whether I call this for each momentum mode, so if you want, I could have just said, or yeah, if I didn't switch language and call it just this, if I just stuck to the way you see it right here, the honest way, then you would have said, the quick way to remember this rule of the epsilon is wherever you see, well, you would have had something that looked like that's what you'd have had. And I get a chance. Hopefully I'll derive this right now, but no matter what the p's are, and the m is always there, this is always positive, epsilon is tiny. Whether I keep this or abandon it is irrelevant, right? I'm taking the limit as epsilon gets small, so for whatever value this is, I'm making the epsilon smaller and smaller and smaller. So, in that sense, we can draw. Okay. That's also the sense here, that whatever these values are, so whether the field is wiggling in space-time or not, and I'm integrating phi to infinity, it's the large phi behavior that this thing is controlling. And it does it no matter what it's not, it doesn't care how the field is wiggling. It's just exponentially damping the large phi behavior. I think I want to do this next, so wait.
So that epsilon in the propagator we found was very crucial for like unitarity and optical theorem.
Yep, yep.
But now we're saying it comes from making the Hamiltonian slightly non-unitary.
Yes, and there's a reason. Because when we make the Hamiltonian, well, one of the things that we're doing with the optical theorem and with, this I epsilon is closely related to the step function that is the Fourier transform, which involves I epsilon. That we all know, that's where it really comes from. And then we see how the I epsilon shows up in the optical theorem and so on. And there's a sort of simple, so it seems surprising, maybe beautiful, but surprising that the same I epsilon is coming back at us from this other way of thinking about a non-unitary Hamiltonian. And the connection is that when I check the optical theorem, I look at that intermediate state and so on. In fact, this state is not, this looks like a pair of free fermions. And if I really had just the Hamiltonian and nothing but the Hamiltonian and evolved backwards in time, it should have just remained there forever. The fact that it was created at a particular time, which is where the step function in time comes from, is where you sort of leak in the statement that the free Hamiltonian, just in terms of the free Hamiltonian, that the free Hamiltonian is not acting unitarily for all time. There's a kind of a fiction to get an perturbation theory gets you an interacting picture by working in terms of Lego blocks which look like free Hamiltonian propagation, but not free Hamiltonian propagation for all time, punctuated by these things called interaction vertices. And so the I epsilon, we all know that step function business that gave rise to the I epsilon, is coming from the fact that the free Hamiltonian is not an operation for all time, it's being only turned on right there. So there's a kind of, in perturbation theory, there's a kind of breakdown of using the free Hamiltonian as time evolution, and that's what this thing is controlling. There's also the fact that, and that's also related to the optical theorem. The optical theorem is sort of looking at that intermediate state, but it's not true that this intermediate state has existed for all time. And so there's, again, the step function coming in. The other thing that is there in all these correlation functions that we calculate is, of course, so time is, let's say time is going this way. This was the vacuum and this was the vacuum. Is still being put into all these Green's functions. Not into the S matrix. So there's a limit of Green's functions which gives you an S matrix. And there the optical theorem continues to play a role. But once again, because secretly it's looking at things that happen between finite time intervals. But the fact that we have the vacuum here and the vacuum here for the general correlation function, and then we have definite sources which turn on and give us particles, is related to the epsilon from this point. We're just trying to ensure that we start with the vacuum and end with the vacuum. So I don't know that I understand it any better than that it is morally related, but it still strikes me as a little bit of a nice miracle that it comes back at you. But you can ask just, you can say, it didn't have to be so, but what a disaster it would be if it was not so. In other words, we have a way of doing the perturbative expansion of this, and getting the correlators, and it definitely involves that I epsilon. And if we do this path integral mumbo jumbo and we end up here and we don't get that, in some way that's a disaster. I mean, in some, it's very much like the situation here is a little bit like the situation with that causality thing, you know, where I did the example of causality and how even though the propagator does not vanish outside the light code, secretly the physics that it describes is causal. And at first sight you say, well, look, it's a relativistic theory. It has to be relativistically causal, so let's not spend any time talking about it. And they say, but how did it do it? How was it so clever? And we play it out blow by blow and we feel we learned something. I would say similarly here, it had to happen. It had to happen. What's surprising you, and I'm equally sort of surprised, is that it happened, it seemed to come to pass in a very different set of considerations. At no point here did we do this sort of perturbative thing. It is a little bit perturbative. The step function in time is coming from the Dyson formula, that master formula of perturbation theory, known as the Dyson formula, is the thing that gives you all these time orderings. And the time orderings because you could bring down the interaction Hamiltonian and then propagate in the free theory, then have another interaction and propagate in the free theory. So that step function is, which gives the epsilon there, is inherently very perturbative. Here we've done something in a form which we hope is sort of non-perturbative. But the same epsilon feature has to show up somewhere. So there's something more to meditate on, but on the other hand, it had to have happened. And it's good as a kind of check of sanity, but you can see where it happened. So I've gone a bit over, so next time I would like to just sort of show you this. I'm just sort of anticipating here.